So this is Lab 5, the Adventure Lab, and for my lab I chose to do the Solar System Lab. The purpose of this lab was to take principles learned from the Black Hole Lab and model the solar system using given data. From this, to model the orbits of each planet in terms of years, and also determine if it can accurately predict the length of a year, month, and day on Earth. As for the results show that they can be accurately predicted. Basic data about the planets was gathered from this website. I included Pluto because although it's technically not a planet, the website provided the data for Pluto. And also, it's important to note that for the code that I show later, that delta t is equal to 24 times 60 times 60, which is the number of seconds in a day. The physics principles that apply to this lab are Newton's second law, along with the use of the gravitational force equation, which is the negative gravitational constant times mass 1 times mass 2 divided by the magnitude of the distance squared times r hat. This equation is represented in the VPython code, which is equated to the net force. Newton's second law is applied, of course, because with the data I can use the distance between the planet and the sun to find the magnitude of r and r hat. With these values I can find the gravitational force. The gravitational force is the only net force. So now that we have the net force, we can find the momentum of the planet. The change in momentum is equal to the net force times delta t. Now we can find the position of the planet, which in this case is Mercury, by setting the change in position equal to the velocity times delta t. Since we don't have velocity, we can divide the momentum by the mass as shown in the code. This last line of code helps draw or trace the orbit. And it's also important to note that this block of code was used for every planet. So some of the assumptions made for this lab was that the momentum and position of the sun would be 0, and the planets would orbit in a circular orbit, which in reality they don't. As I showed earlier how Newton's second law is applied, here is the rest of my code. All I did was simply put in the position of each planet relative to the sun, trace the orbit. I implemented the mass of all the planets, and I found the momentum of each planet by multiplying the mass times its orbital speed, and I traced the orbit. This is where Newton's second law for all the planets was applied. This is part of the model when the code is ran. Now the lab question proposed to us was whether the model could accurately predict the length of a year, month, and day on Earth. Time can be found by dividing the distance by velocity. So in the case of an orbit, t equals 2 pi r, which is the circumference, divided by velocity as represented in the Python code shown. I divided by 12 to represent the number of days in a month, and it would be pointless to show the number of days in a day, so I multiplied by 24 to show the number of hours in a day. Python shell, this is what was displayed. These values are relatively accurate, however, of course, there is some deviation, because the data retrieved may not be 100% accurate, distorting the data. Also, rounding error. The first number represents the number of days in a year, the second number represents the number of days in a month, and the third number represents the number of hours in a day. As we all know, different planets take different times to orbit the sun. Here is how long it takes each planet to orbit the sun in terms of Earth days, on the left side. Using the same equation to find the time it takes Earth to revolve around the sun, the same data was found for each planet, and these are the results for the number of days it takes each planet to revolve around the sun in days. This leads us to a what does it mean question. So as we saw, the model produced numbers that are relatively accurate to how long it takes Earth and the other planets to revolve around the sun. There is some variation between the predicted values and theoretical values. For example, it takes Earth 365.25 days to revolve around the sun, but the model predicts 366.05 days. The difference may be due to the negligence of gravitational force between planets and between each planet and its satellite. This concludes Lab 5.